We are now ready to tie everything together. We're going to start with an example. So we're going to consider the system of three equations in three unknowns: x plus 2y equals 11, y minus 2z equals 12, and negative 3x minus y plus 6z equals 11. If we represent each column of coefficients and the augmentation as vectors, then we have v1 is 1, 0, 3, v2 is 2, 1, negative 1, v3 is 0, negative 2, 6, and the augmentation b is 11, 12, 1. We know that finding a solution to this system is equivalent to finding an ordered triple x, y, and z such that x v1 plus y v2 plus z v3 is equal to b. So if we assemble our vectors v1, v2, and v3 into the coefficient matrix A, whose columns are v1, v2, and v3, and our unknowns into the three-dimensional vector x with entries x, y, and z, then we know the left-hand side of this equation is equal to A, the matrix, times x, the vector. So we can think about solving the system as being equivalent to solving the matrix equation ax equals b for the three-dimensional vector x. So there's nothing really new here aside from a perspective. We simply have to place our system in the form of an augmented matrix, then use Gaussian elimination to solve the system. So first, we can add 3 times row 1 to row 3. Next, we can subtract 5 times row 2 from row 3. Then we can scale row 3 by 1 over 16. Next, we can add twice row 3 to row 2. And finally, we can subtract twice row 2 from row 1. So we see that our system has a unique solution, which we've previously identified as the point negative 9, 10, negative 1. From our new perspective, we can think about the matrix equation ax equals b as having a solution that is a single vector negative 9, 10, negative 11. We can also think about this as allowing us to express b as the matrix vector product, which remember is equivalent to expressing b as a linear combination of the columns of our original coefficient matrix A. In fact, for any linear system with m equations in n unknowns, we can translate each of the columns of coefficients into a vector. We can arrange those vectors as a matrix, and we can combine all of the b's on the right-hand side with the augmentation and express our linear system as brackets A and then B. So an ordered n tuple, C1, C2, down to Cn, is a solution to the linear system if and only if A multiplied by the vector C1, C2, down to Cn, which remember is defined to be the linear combination C1v1 plus C2v2 plus ... plus Cnvn is equal to b. So let's talk about an example. Describe the solution space to the matrix equation 2, 4, 1, 0, minus 1, 3, 2, 6, minus 5, multiplied by the vector x is equal to 0, minus 5, 15. So the important fact from above is the set of vectors x, which will satisfy this equation, are given by solving the augmented matrix 2, 4, 1, 0, minus 1, 3, 2, 6, 5, bar 0, minus 5, 15. First, we'll interchange rows 1 and 3. Next, we'll subtract 4 times row 1 from row 2. Next, we'll subtract twice row 1 from row 3. Then we'll scale row 2 by negative 1 over 13. And we'll scale row 3 by negative 1 over 6. We can see now that rows 2 and 3 are the same. So when we subtract row 2 from row 3, we'll get a 0 row. Finally, we'll take 3 times row 2 and subtract that from row 1. Now that we're in reduced row echelon form, we can think about our unknowns as being x, y, and z. So we get two equations. The first row tells us x plus z is 0, and the second row tells us y minus 2z is 5. We can use the variable z as our free variable. X and y will be our basic variables. So we get a parametric description. X is the same as minus z, and our y coordinate is 5 plus twice our z coordinate. We can translate these parametric equations into a vector equation parametrized by z, simply replacing x by minus z and our y coordinate by 5 plus 2z. We get the vector negative z, 5 plus 2z, z. Now, we can break this apart as two vectors that are added together. One will have z's, the other will not have z's. So the vector without any z's in it is 0, 5, and 0. And our second vector is negative z, 2z, z. We can think about this vector as a vector with entries negative 1, 2, and 1 that's been scaled by z. Since we are allowed to choose any z that we like, we can see that the solution to our matrix equation is actually a line sitting inside of R3. If we name these two vectors v and w, then we can describe this line as the set of all vectors v plus z multiplied by w such that z is any real number. That is to say, from this new perspective, it's much easier to identify the solution space to a linear system of equations as a geometric object rather than some sort of abstract set of points.